it's essentially the same as taking derivatives, but taking derivatives to an infinitely dimensional function. So it is asking if my u of x is going to be perturbed a little bit into u of x plus an infinitesimal delta u of x, right? Delta u of x is a function of x. It's an arbitrary function of x, but it's infinite dimensional because delta u of x can be any value anywhere as long as it is infinitesimal. Okay. How much does that change the objective function c plus g? All right, so let's actually plug it in. My c plus g, g plus e is going to be changed into integration from 0 to 1 of g rho of x. Note that u has changed into u of x plus delta u of x, right? Okay, and then plus t times du dx also has changed into du dx plus d delta u dx, or the derivative of this infinitesimal perturbation to the function u. All right, so this is the thing that is integrated. All right, so now is the time to ignore the squared of this infinitesimal perturbation, because if the perturbation is infinitesimal, okay, then the square of this infinitesimal perturbation is infinitesimal squared, and that can be ignored. All right, so this is equal to what? I mean, let's actually, because we already have this term, so this term and this term squared can actually come out to be my g plus e, and then we only need to track the perturbation. Plus integration 0 to 1 g of rho x. You see delta u of x, okay, plus t times, okay, so here's the important part. We get 2 times du dx times d delta u dx. All right, agreed? So here, I'm basically expanding the square, and du dx squared already is here, so that gets lumped into g plus e. And the square of the delta u term is neglected, so the only thing we left is the cross term, 2 times du dx times d delta u dx. Okay, let's continue. That works. To make this work. Oh, anyway, okay, so all right, so what we had here is that due to a perturbation delta u, g plus e has changed by how much? Okay, by integral from 0 to 1 rho x g times delta u plus t times 2 du dx d delta u dx. Okay, so what function u, okay, which appears here, would minimize g plus e I mean, if you turn that into a minimization problem, and the first order optimality condition ensures that no matter what small perturbation you make to the function, you would not further decrease the total energy, right? That's the optimality condition. No matter how you change my u, you would not decrease the total energy. So what kind of u would ensure that no matter what delta u is, you wouldn't decrease the total energy? Here, in order to derive this, we actually have to get the delta u out of the derivative. How do we do that? We use a method called the integration by parts. Okay, what integration by parts does is that actually it's pretty simple. So if you have a function f and g, okay, so let's say you have a f of x times g of x, okay. If you integrate, if you take the derivative of them with respect to x, you get f times dg dx plus g times df dx, right? Okay, and if you integrate both parts in x, you know, through the fundamental theorem of calculus, right? What you get is the left hand side becomes fg, right? If you integrate over a fixed interval a b, you get f of g a b, and the right side you get integration a b of f dg dx, and g times df dx. Okay, this is actually seems like a trivial manipulation, but in reality it's actually something very handy, because you can, if you have a function multiplied by a derivative of a different function, you can take g out of the derivative by, you see, like if you just move one term to the other side, you can take g out of the derivative and put f into the derivative. In this case, if you apply this to here, if you think of delta u as the g here and du dx as f here, you can take delta u out of the derivative by putting du dx into a derivative, right? Into a second derivative. Okay, so this means that I can write this as rho g delta u plus t times 2 times, well, I need to have a minus sign, right? Because in integrated by parts, what I moved du dx into a derivative, it becomes a negative of a second derivative times delta u dx. And then I have the boundary term. The boundary term is t times 2 times du dx times delta u, 0 and 1. All right, and because again, coming from the physical problem, my delta u at 0 and 1 has to be 0, so this term goes away, and what I have is integration from 0 to 1 delta u times a differential equation. Oh, actually minus 2t d square u dx square. And in order for, remember, this is the change in the total energy due to a small perturbation delta u. And the change has to be 0, right, for any potential delta u, which means what is multiplied by this delta u has to be 0 everywhere. So we have derived a differential equation. That's rho g is equal to 2t times d square u dx squared.